All right, grade 12s. Well, good morning. As I record this, it's still snowing pretty heavily outside. I don't know if it's going to be a snow date or not tomorrow. It's Sunday night right now when I'm recording this, but if it is, then maybe a whole bunch of you, maybe the whole class is listening to this live video. So good morning, everyone, and welcome to winter. All right, so I'm going to get right to it. This is still review from stuff we did in grade 11, but I'll go quickly through it. All right, so here's the deal. I want you to recall a couple of things. Number one is Newton's second law. So here we see the mathematical expression of Newton's second law. I wrote it earlier, okay? And it says here that F net equals mass times acceleration. F net is the sum of all forces acting on mass m, okay? And here you can see mass m in the formula, and you can see it over here, okay? So whatever the mass is, the object, it's experiencing several forces, let's say. The vector sum, and I might as well include the word vector, the vector sum of those forces, okay, is the net force acting on the object. Now, sometimes we write it like this, you know, they write the sum of all forces equals F net, where this sigma notation here means sum. You'll learn about that more in university math, okay? But that is the sum of all forces. Now, the whole point is that it's the vector sum. So sometimes you can get a sum of zero, even when there's several non-zero forces acting on an object. Okay, now A, of course, is the acceleration of mass m, and that's Newton's second law. Now, Newton's second law, crucial for first-year university problems, and they can actually get surprisingly difficult, even though it's a very simple formula. Sometimes working out what the net force is or creating an expression for the net force involves solving several equations. So we'll talk about that, but it's all about, at its core, it's a simple concept, but in practice, it can get a little tricky. All right. Now, what kind of forces will we see in problems like this? Well, let's remind you what how gravity works near the Earth, at least. And what I mean by near the Earth is basically anywhere where you can stand on the Earth, anyway, up to, and you know, up to the top of Mount Everest and down to the depths of Death Valley. Okay, you know, you're standing on the surface or in a mine or even in an airplane, close enough to Earth's surface that the gravitational field is not affected very much. Okay, and anywhere within 10, 20 kilometers of Earth's surface, you are looking at around the same value for the acceleration due to gravity, which is 9.8 meters per second squared. And of course, you know that direction is down. Now, I have a little picture of the Earth. You know, I apologize to you flat earthers out there, Matthew, okay? But look, wherever you happen to be standing, down is kind of a relative concept. So if I'm standing up here at the North Pole, you know, whatever, imagine this guy standing here, then down is actually sort of towards the south, okay? But actually, of course, into the ground beneath him, okay? Not south across the surface of the globe, but towards the center of the Earth. And of course, if you're standing over here, of course, flat earthers don't believe this, right, Matthew? But if you're standing over there, towards the center would be, you know, in a kind of a different direction, but still towards the center. We all agree it's towards the center. And in fact, if you're standing here on the bottom, you'd be kind of upside down compared to the guy standing at the North Pole. But the force of gravity would still be down into the earth beneath your feet towards the center, right? So it all sort of depends on where you're standing, what direction down really means. But we can all agree if we point towards the floor, that is down, okay, no matter where you're standing here. Okay, so those vectors here, those blue vectors they see on the outside of planet Earth, all pointing towards the center of the planet. And that is the direction of the force of gravity near the Earth. Well, because of Newton's second law, we can therefore say that the force of gravity on an object is just equal to mg, and we'll say A equals G equals 9.8 meters per second squared. And of course, the direction is down. Okay, now we did this last year, no surprises there. So we used the letter G to represent the acceleration due to gravity. And really all we're doing to get this formula here, is we are using Newton's second law, okay? and let's say we pretend that gravity is the only force acting on the object, well, this is how you would calculate the magnitude of that force. Okay, and since all objects accelerate at 9.8 in the absence of air resistance, okay, then all forces of gravity can be factored or determined this way, okay, using that simple equation. All right, now let's talk about the normal force. Now, this is a much misunderstood force. A normal force is about surface contacts, okay? Now, there are many different types of surfaces, like the tabletop is a surface, the floor is a surface, the wall is a surface, right? Your hand, the palm of your hand, you can consider that a surface, okay? Now, whenever an object is in contact with a surface, that contact force we call the normal force. And the reason why we call it the normal force is because it acts, this word normal means perpendicular to the surface. Okay, so right now, I imagine you're in contact, at least in some sense, with the floor, okay? And the floor will push up on you. Now that upward force is perpendicular to the surface of the floor. And that's what surfaces do after all. They can only push. Now I've got a little diagram of it here. Okay, so the normal force is perpendicular to the surfaces in contact. So here we see a table. Okay, so here, I'll highlight it in yellow. Here's the table right here. Now that table can only push on the box. It can't pull it. Okay, it pushes. Now actually the box, the bottom of the box is also a surface, right? So the box is making a surface contact with the table, and this is the normal force, which I will call Fn, of the box on the table. So the table is an object too, and it's experiencing a force of contact because of the bottom of the box touching it. Well, here, this normal force is the one caused by the table on the box. So the box, both the box and the table both have surfaces that push. So in this case, the bottom of the box pushes down on the table, but the table, the top of the table, pushes up on the box. Okay, and this is how normal forces operate. Now, these two forces, this is Newton's third law, these two forces are an action, reaction pair. Remember how Newton's third law is for every action, there's an equal and opposite reaction? So these two forces would be equal and opposite, okay, according to Newton's third law. In other words, the force of the table on the box would equal the force of the box on the table. And that it just in opposite directions, okay? So we call that an action-reaction pair. I know the arrows don't look like they're the same size, but just ignore that for now. So that's a normal force, okay? The key point is surfaces can only push. They can't pull, okay? Your hand can grip something and pull on it, but a normal, like a tabletop surface, like that kind of surface only pushes, and it pushes in a perpendicular sense to the orientation of the surface itself, okay? So, you know, here, if I put like a box on a surface, the normal force would be upwards, and the force of gravity would be downwards. And very often these two things balance each other out, and you get a net force of 0, okay? So, but that's not always the case. If you remember in grade 11 when we did elevator problems, in the elevator problem, occasionally the normal force was not equal to the, it depends, right? If there's acceleration involved, then we use Newton's second law and we can work it out. But the force of gravity on someone does not depend on whether you're in an elevator. It's just mass times 9.8. But if you're accelerating up, that normal force will increase. If you're accelerating down, it will decrease to give you acceleration either up or down, okay? So that's surface contact, normal forces. We did it last year, so moving on. Now, applied forces. Applied forces are other types of contact forces. They can be pushes or pulls. So, you know, like let's say, for example, you have a person Okay, let's say it's Muriel here, and she is pulling her cart full of goodies, okay, and she's pulling it, you know, in this direction, okay, and let's treat the cart full of goodies like here's the goodies in here, who knows what they are, okay, just bring them to the class. Now it's during COVID, so maybe like she's wearing a mask or something, you know, or whatever, okay, and it looks kind of weird now, but there you go, there's Muriel wearing her mask, doing the right thing, okay, for the COVID-19 pandemic. And let's give her some acceleration. Let's say she's speeding up in that direction along with her cart full of goodies, okay? Anyway, if you draw a diagram of this box, okay, of this object here, okay, then that diagram, we call this a free body diagram, more on this later, free body diagram. Of course, there's gravity acting on it. And we know there's a normal force because it's sitting on the floor, and so that will exert an upward force. But she is pulling on it. We call that pull the applied force. In other words, she's exerting a contact force that's applied to the object, in this case, the handle of the object, that is pulling it forward. And of course, we would put the acceleration in the x direction like this. Okay. And yes, so applied forces can be, you know, FA can be a push or a pull, depending on the question. In this case, it's a pull, but she could be like behind it, pushing it forward with her hands, right? Whatever. And usually we're talking about some external actor pulling or pushing on an object, okay? So in this case, it's Muriel, and she's pulling her box forward, okay? Now tension, ropes, chains, threads, you know, etc. When you pull on a rope, there's tension in the rope. Okay, it creates tension in the rope, and that tension, okay, can be used to do various things. So here you can see the force exerted by a rope, cable, chain, etc. is called the force of tension. I like using the letter T. Some textbooks, like your textbook, will use F with a subscript T. I like using T, but I think I'll go with your textbook notation this year, and I'll just say FT. Okay, they mean the same thing. Okay, force of tension. Doesn't matter what letter you use, but in the old days we used to just use a capital T for tension, but now I tend to use FT just to be consistent with the textbook and not to make it too confusing. Okay, if slack, so if the rope goes slack, FT equals 0. Okay. Now action and reaction applies to something like this. Okay, so action and reaction would mean something like this. Let's say you had a cart that was connected to another cart. And then here we have Muriel once again. Okay, there she is. Here, I can't get her smiling there. There she is smiling. Okay, no mask this time. I guess she's by herself. Okay. And if you look at this rope here, so let's look at that second rope. You will see, if we call this one mass 1 and this guy mass 2, what you'll see is mass 1, its free body diagram looks like, whoops, sorry, the force of gravity, fix that. Force of gravity, a normal force, and then there is the force of tension pulling it forward. Let's call it the force of tension, 1, because it's applied to box 1. So that's the free body diagram of this guy, and of course he'd be accelerating forward like this. But if you draw the other box, what you would find is that there's 2 tensions acting on the other box. Oops, I didn't mean to draw the wheels. Just free body diagram, no features on the object, just a box, right? So there's gravity, there's a normal force, there is force of tension 2, that's this rope pulling it forward. It's accelerating that way, same as everything in this problem. But then there's also force of tension 1 pulling it back. Okay, pardon me for erasing the box. Force of tension 1 pulling it backwards. Now, these two forces I will highlight in yellow are also, okay, so this is mass 1, this one is mass 2, okay? And I just want to tell you, since, like, you know, here, I'll put it above here, mass 1, mass 2. So these are two different masses, right? Now, what I've highlighted in yellow, those two forces there are an action-reaction pair. They must be equal, but opposite. So they must be the same size, but in opposite directions. See? Newton's third law, all forces occur in pairs. Okay, and for every action, there's an equal and opposite reaction. So if mass 2 is pulling mass 1 forward, then it's only logical that mass 1 is pulling backwards on mass 2 with that same rope. So the tension in rope number, we'll call that rope number 1 and rope number 2 here. The tension in rope number 1 would be experienced equally by both mass 1 and mass 2, just in opposite directions. Okay, so they're both accelerating forward though. Okay, so this tension here must be greater, the second tension must be greater than the first tension in order to overcome that backwards force. Anyway, more on this later. You can see how it gets complicated though, right? So tension in ropes, we're going to look at pulleys this year. We didn't really do that last year. And understanding the concept of tension and how the tension is the same everywhere in a rope, crucial. Okay, but we'll talk more about that later. All right, let's get to everyone's favorite, which is surface-on-surface friction. Okay, now friction depends on two things, basically. Okay, it depends on exactly two things. One of those things, okay, if you look at this object, there's gravity acting on it, and there's also a normal force. Okay, so this guy here, the normal force, that one, okay, is the amount of contact on the surface, okay, from the surface of the object. Now here, the surface is rough, which is the thing that creates friction in the first place. Now, frictional forces can be resistive, but static friction may not be resistive. It could be actually helping you to move. In fact, that's how you normally walk. You walk with static friction. Okay, and actually it's not a resistive force in that case. In fact, it's a propulsive force. Cars drive by static friction. You walk with static friction. In fact, anything that rolls along the floor, okay, or skitters along the floor, anything like that, okay, whatever its method of locomotion is, I guarantee you it's using static friction to do it. Okay, the exception would be anything that flies, okay, like birds, planes, hovercraft. Okay, they're not touching the floor though in order to propel themselves. So that's a very different phenomenon. But if you are a walker and you walk along the floor, you're using static friction. Now we did this last year, but maybe some of you are, you know, need your memories refreshed. So you either did this during the pandemic or you did it a year ago, okay, or over a year ago now. So let's jog your memory, okay? How does kinetic friction work? Well, kinetic friction depends on two things. Those two things are roughness. So how rough the two surfaces are. And there are always two surfaces. There's the floor, but then there's the box, which has a bottom surface on it. Okay, so we're going to call this thing that determines sort of the property of roughness, we call the coefficient, of friction. So I'm going to say mu k is the coefficient of kinetic friction. And it's a measure of how, relatively speaking, rough the two surfaces are. Okay, it has no units. That's why we call it a coefficient. Coefficients have no units. Okay, now the other thing that friction depends on is the normal force. Okay, how much contact? Between the surfaces. Okay, whoops, spelled that wrong. Trying to do this quickly. All right, so here's the deal. Therefore, putting it all together, the force of kinetic friction, so we write Fk, equals the coefficient of kinetic friction times the normal force. Now, very often, and in almost all problems in grade 11, the normal force is just equal to the force of gravity. That's going to change occasionally this year. So remember, you just have to find the normal force and multiply it by the coefficient of friction. That's how much kinetic friction you have. And this one is always a resistive force. Kinetic friction is when you're skidding, okay? So it's a resistive force against the motion of the object, okay? Now let's go to static friction. Static friction is a bit different. This is where, okay, like here, with kinetic friction, you have slipping or skidding. And therefore there's waste heat being created by that process and you're losing energy. But static friction is the very opposite. There's no slipping or skidding, right? Okay, no slipping. So the point of contact between the two surfaces does not slip. Now, when you walk across the floor, you're moving, okay? This does not mean there's no motion. You're moving, but not slipping. Okay, and in fact, you're using static friction to propel yourself forward. Okay, so that's what static friction is all about. Okay, now it turns out that the maximum force of static friction, so let me write it like this, force of static friction, and I'll put in brackets max, okay, the maximum possible value is equal to mu s Fn. Again, it depends on similar things. This has to do with roughness, except it's not measured. It's never exactly, well, so it can be equal to the two coefficients can be equal for the same two surfaces, but not necessarily, okay? And this is the normal force. So this is how much contact you get between those two surfaces, right? Now, the thing about static friction is the actual force of static friction is usually just a matching thing. So the actual force of static friction can be written like this. It's less than or equal to the coefficient of static friction times the normal force. Okay, and what does that mean? Well, what it means is, you know, if you have a person, okay, that is pushing a box, okay, and let's say here's our friend, here, let's pick on someone else. Let's pick on, gosh, off the top of my head, who? Let's say it's David, okay? There's David. He looks a little grumpy there, doesn't he? Come on, David, it's physics. Cheer up, okay? Anyway, let's say David here is pushing, and he's pushing with a force of 20 newtons, okay, on this mass, and it's not going anywhere. Okay, so this is his applied force. And the question is, how much static friction is there? Well, there's no motion, so acceleration is 0 in this case. So therefore, the force of static friction, what's it equal to? Well, we know it's 20. So this is to the right, the force, it's 20 newtons. To the left, and how do we know that? Well, because we know the net force has to be 0. Now, notice I did not use this formula when finding that answer, okay? In other words, the force of static friction often just matches whatever the applied force is. What this is telling you, what this formula tells you, is when you reach the maximum, this tells you what the maximum force could be until it'll just start to slip. So I'm just going to say when the force, applied force, equals mu s Fn, it will therefore just start to slip, okay, or skid. Now that it's snowing outside, okay, one thing about a road that's covered with snow is that it decreases the coefficient of static friction. And so tires depend on static friction in order to propel the car forward. So what the motor does in the car is it turns the wheels so that they roll forward, but then the static friction between the wheels and the road propel the car forward. That's how it works. Now, if you decrease the coefficient of static friction because the road is full of snow, then what happens is the wheels will start to skid much easier. And so you see people skidding all the time. Now, winter tires are kind of cool. The rubber in the winter tires stays soft at low temperatures, and that improves your static friction coefficient. Okay, now in the summer, they're too soft, and so they'll wear very quickly in the summer, these winter tires. That's why you need two different kinds of tires. One that's better for warmer temperatures and one that works at colder temperatures. So that's what winter tires are all about, working at colder temperatures. And the thing about rubber is it adheres to the surfaces of contact and therefore creates a lot of friction. Now, if you're trying to drive across a snowbank, you're going to decrease the contact force also because the snow will lift the car. And then you get two problems. You know, number one, you've lowered the coefficient of static friction because of the snow cover. Two, you're lifting the car and decreasing its normal force. And those two things will mean less static friction, and it means the car will just, you just spin in your wheels. If you've ever seen anyone do that in the winter. Okay, you'll see that this snow continues like this, like it's coming down even harder right now since when I started. You'll see a lot of that tomorrow, I think. All right, so here's the deal with static friction. I've got a little graph of it here. Okay, so here's the deal. When you use the formula, like, and here's an example, let's say the coefficient of static friction is 0.5, okay? And let's say the normal force, which here they write as a capital N. I'm gonna write that as Fn. I don't like writing as a capital N because it looks like the unit of newtons. That's not right. So let's cross out that, put the normal force in there, okay? So in this case, let's say that the normal force on the object is 100, okay, newtons. So that's what they're telling you here, that the force of gravity is 100 newtons, and therefore the normal force is also equal to 100 newtons because it's a horizontal surface and it's not accelerating up or down, okay? In fact, no acceleration at all. Now, you're pushing on the object with this applied force. You're pushing, pushing, pushing. Like here's David, right? Pushing, okay, on the mass. So David tries pushing here. Fix his hair a little. Like a little expression. So here's David pushing on the mass. He's pushing it forward, okay, but he can't make it move because you know what? He's weak, okay? He's not overcoming the force of static friction. Now, all he has to do is push until like he reaches this point here. So once he applies 50 newtons, which is equal to the coefficient times the normal force, right? Once he reaches 50 newtons, it's going to start slipping and moving. And then what will happen is this static friction will quickly become kinetic friction as it starts to skid. And the coefficient of kinetic friction is only 0.4. So now he's pushing with 50 newtons. It starts to accelerate because with 50 newtons, there's only 40 newtons of resistive friction, kinetic friction, opposing him. So there's a net force of positive 10. So it starts to accelerate forward. Okay? So that's the deal. Now, if he pushes with less than 50 newtons, then here's the thing, static friction force just matches the applied force. So if he pushes with 20 newtons, then the static friction will be 20. If he pushes with 30 newtons, then the static friction will be 30, 40 and 40, 45 and 45, right? Once he reaches 50, it'll just start to slip, and anything past 50, it'll skid, and now you get some acceleration, okay? So I like this graph. I think it explains it well, and that's it. All right, so that is just a little bit of a lesson on these types of forces. I'm going to continue this right now because there is a second part to this. At first, I was going to make a separate video. Actually, you know what? I'm going to make a part 2. Okay, I'm going to make a part 2. So now that we've examined the different kinds of forces, let's see how we solve problems like this. So in the part 2 video, it's going to be on free body diagrams. The reason why I'm going to make it separate is because that's a really crucial lesson. So you can always just go back and just get that part of it. So let me stop this here, and I will post 2 separate lessons today, and the next one will be on free body diagrams. All right.